I forgot to record this. I forgot to record this, but the recordings for the morning class is available. So if there's a big gap there, check the morning video. We talked about the same thing. How would you name this? Phosphorus, not tetra, but phosphorus trichloride. Trifluoride, sorry. Phosphorus trifluoride. I'm gonna name that. Phosphorus trifluoride. All right, let's go to this next problem. Actually, we didn't get this far in the morning class. Okay, so let's say we have an unknown substance. Well, actually, this is a known substance. They tell us what the substance is. They're saying it's nicotine, but let's say this is unknown. We send it out for analysis. The results from the analysis come back. It's 74.1% carbon, 8.64% hydrogen, and 17.3% nitrogen. And so we're given the percent by mass compositions. And therefore, we have to do an additional step in that chart. And that additional step is we want the grams of each. And so what do we do? If we're given the percent by mass composition, then we make an assumption. What do we assume? We assume 100 grams. Therefore, if we have 100 grams, then we have 74.1 grams of carbon, 8.64 grams of hydrogen. Should that be H2 or H? It should be H. And 17.3 grams of nitrogen. Is that N2 or N? It's N. Yeah. And then what do we do with this? Do we want the mass ratio or do we want the mole ratio? We want the mole ratio. Chemical formulas are mole ratio, so we need to convert it to moles. And so here we're going to convert the carbon to moles by using the molar mass of carbon. Molar mass of carbon is 12.01 grams of carbon per mole of carbon. That gives us 6.17 moles of carbon. Then we go on to hydrogen. 8.64 grams of hydrogen. In this case, we want to use 1.008. We don't want to use 101 because 101 will limit this to 3 sig figs, although it doesn't really matter that it's 3 sig figs. But to minimize round off error, we'll just carry 4. One more than the given. It gives us 8.57 moles of H. I usually carry that one more digit, rounded at the very end. And then we had 17.3 grams of nitrogen, 17.3% nitrogen. This is the mole of nitrogen atoms weighs 14.1 grams, 1.23. And so this is the mole ratio here. It would be C 6.17, H 8.57, N 1.23, but that's not a very good ratio. We want simple whole numbers. So what's the next step here? Yeah, divide by the smallest, which would be 1.23. It's 1.23. When we divide by the smallest, we get about 5 C's, about 7 H's, and about 1 N. So the formula comes out C5H7N. So now that's the empirical formula. If we want the molecular formula, we don't know. It's a molecule of nicotine. This is the simplest whole number ratio, 571. Well, then we have to compare. What do we have to compare to determine if that's the molecular formula or if the molecular formula is different? We have to check the mass. So how much does the empirical unit weigh? We have 5 carbons. And so that's 5 times 1201, which gives us, what does that give us? 60.05. And then we have, how many hydrogens? 7 hydrogens. 7 hydrogen is 101. That's 707. And then we have 1 nitrogen. Nitrogen is 1401. 1401. 1401. And so an empirical unit of this was going to weigh 12, 13, 0, 7, 4, 11, 8, 8, 1, 13. That's the empirical mass. What does a molecule of nicotine weigh? They don't tell us here, so I'm going to look it up. What does nicotine weigh? So let's go to Wikipedia. Take a look at nicotine. A molecule of nicotine weighs 162. We got 81. And so is the empirical formula the same as the molecular? No. The molecule weighs twice as much as this. Therefore the molecular formula has got to be double it. And so it's got to be C10H14N2. It's not the simplest whole number ratio, but that's what the molecule is. And so when I look at this, the Wikipedia, we see C10H14N2. We want the molecular formula. We don't want the empirical formula for this because we want to know what the whole molecule is. And so we have this. Go back here. And so basically all we're doing is we're comparing the masses to figure out, do they match or are they different? If they're different, then well, where are they different? Your book, what your book is going to have you do is he's going to have you do something a little different. Determine the empirical formula of the compound, calculate the molar mass of the empirical unit, determine the molar mass of the compound. Determine the molar mass of the compound is given. You know, that 182U came from where? That 182U, that came from the mass spectrometer or some other technique. There are other techniques that we could use to weigh molecules directly. So that's the mass spectrometer. This one came from calculation. This is the empirical mass. If that came from the mass spectrometer, then this is the molecular mass. And what the book suggests doing is this: divide the molar mass of the molar mass is different than molecular mass. Molecular mass is in U. We'll do it in U because we're weighing individual molecules. Let's say this is the average. And so what we do is we'll take the molecular unit, 182U, divide it by the empirical unit, 81U, and we'll get N. In this case, N is about 2. And that means that the molecular unit is about 2 times. Molecular unit is twice as big, 2 times bigger than the empirical unit. It actually comes out to 1.99 something, which we can round to 2. If I want to be more precise. But anyway, it has to be a whole number multiple. It's got to be 2 times bigger, 3 times bigger, 4 times bigger. It has to be a simple whole number factor. So let's take a look at this example here. A compound with empirical formula C2H5 has a molar mass of 58.12 grams per mole. So we have 1 mole. Find the molecular formula for the compound. So first, we got to get the empirical mass. Empirical mass, we've got 2 carbons. That's 2 times 1201, which is 2402. And then we have 5 hydrogens. 5 hydrogens, 5 times 101, which is going to be 505. And so the empirical unit's going to weigh 29.07. They're saying molecular mass or molar mass. It doesn't matter. They're the same number. So the empirical unit weighs 2907 U or grams per mole, U per unit. Find the molecular formula. Okay, versus, okay, this is the empirical mass. When I look at the molecular mass, what is it? Well, the empirical mass is that. The molecular mass is 58.1 U, 12 U. And therefore, the molecule, can you just see it right now? The molecule is actually got to be twice as big as the empirical unit. What they're going to do is they're going to do the division. So they do the division here, 5806 divided by 2906. I didn't do this very precisely. I just got a ballpark because it's got to be a whole number here. If I were to do this precisely, I would have done 1. Actually, what is it? The nicotine. Let's just do this one more precisely. If I do this one more precisely, I got 58.12. There's some kind of mistake here. This should be 58.12 because that's what was given. So either that one's wrong or this one's wrong. I don't know which one's wrong, so I'll just take that one as correct. This one's wrong. 58.12 divided by 2906. That's perfect. It doesn't always come out this clean. This is 2.000. Usually comes out to like 2.01 or 1.99 or something like that. But that's too perfect. All right, those are some chemical formula relationships. Let me move on to this chapter. Chapter 8 deals with chemical reactions. So what we want to do is, okay, we know the composition. We know a little bit about the structure. And so we want to correlate that with, composition should be correlated with structure, which should be correlated with properties. So one of the properties that we're very interested in are chemical properties. What kinds of chemical reactions will undergo? The chemical property is going to be expressed in terms of a chemical equation, but usually we're looking for evidence of a chemical change. Evidence of chemical change would be change of color. A change of color could be dilution. So for example, if you add a whole bunch of water to this, the color changes. Is that a chemical change or a physical change? If I add water to this, it would be a physical change. It's just dilution. And so we want a more significant change of color, if available. If not, then we look for other things, like formation of a solid product. So when you freeze water into ice, you're forming a solid product, ice. Is that a chemical change or a physical change? That's physical, freezing water. So we're looking for a different type of solid formation. A different type of solid formation would be something called precipitation. So let's show you a little video on precipitation here. This is not. It is hung up. So, okay, this is salt formation. So we have two liquids here. We'll mix them together. Do you see that? That cloud there is actually tiny crystals, tiny yellow crystals. So there's a color change as well, as we're going from colorless to yellow. And that solid's eventually going to settle on the bottom of the test tube. Here, okay, that's called precipitation. The color change there and precipitation. Let's move on to the next one. Next one is called formation of gas, which we call effervescence. It's not boiling water. Boiling water is not chemical. And so let's take a look at effervescence. Would be like Alka-Seltzer is actually a chemical reaction, so let's take a look at that. This is Alka-Seltzer. Dump Alka-Seltzer in there, and then you can see the gas bubbling out, filling up the balloon. That's called effervescence. Okay, then let's see. Next one is this, absorption of heat. Absorption of heat is called endothermic reaction. It absorbs endothermic reaction. And so if it's endothermic, it's going to get cold. That could be physical or it could be chemical. It's hard to tell. If it releases heat and it gets warm, it's called exothermic. So we have endothermic, exothermic. And then finally we have light emission. Light emission. Like when you burn methane, you get light emission. And so here's a color change, but this color change is not due to pollution. You can see that the volume doesn't change starting from here, but the color did change. It faded, so that's evidence of chemical change there. This is, what was this called? Yeah, but in this case, we're not precipitating a yellow solid, we're precipitating a white solid, like a cloud. What was this called? Effervescence, good. What was this called? Well, this is heat. Heat is going to be exothermic, and so this is going to get hot. And the other thing is we see light, evolution of heat and light. When we see light like that, it's called emission, light emission. This would be an example of light emission. A cold pack like this would be an example of a endothermic reaction. But you have to be careful because these cold packs might be a physical process. Sometimes physical processes do lead to temperature drop. Yeah. All right, so let's take a look at a chemical reaction really quick here. That much time. Well, let's take a look at methane. Methane can react with oxygen. This is a combustion reaction, so we'll see. And thus produces CO2 gas and H2O liquids. H2O liquids here. Yeah, right there. And so over on the left, we have the reactants. And so these substances react, and in a chemical change, what happens is the atoms get rearranged, and we form new substances called the product. We have things called the subscripts here. The subscripts we can't change. So for example, it's a 1:4 ratio. And so the subscripts are the mole ratios of chemical formulas that we were talking about. And so if I change that, let's say it went CH8, then it's no longer methane. You know, so we don't touch the subscript. However, these we can touch, like this 2. What does that 2 mean? Well, the 2 is a coefficient. And the 2 we can change because that 2 just represents having 2 of these oxygen molecules. So we have 1 methane. And the methane is going to have a carbon in the center, and then these hydrogens come out. And this is called a wedge dash diagram here. It kind of looks like a ball-shaped type deal. And then we have 2 oxygens. The oxygens look like this. And there are going to be 4 dots on each oxygen. And we'll talk about those later. But for right now, just draw like this. And so this coefficient 2 means I have 2 of these O2 molecules, and each O2 molecule is like that. Okay, what's going to happen in a chemical change is the atoms get rearranged. And here on the carbon, now we don't have any more hydrogens. We're going to put 2 oxygens on there. Don't worry about the structure of this yet. We'll talk a lot more about the structure. And then these hydrogens go to the oxygen like this. Here. And so we rearrange the atoms. And so there are 4 hydrogen atoms originally on the carbon, and but we only have 2 here, and so I'm missing 2 hydrogen atoms. If I'm missing 2 hydrogen atoms, we say it's not balanced. And so one way to fix that is I'll just make this an H4O. Can I make it an H4O? I can, because H4O, what the heck is that? And so what I have to do is I'll have to have 2 H2Os. So if I go 2 H2Os, then I'm good. That's good. And so I have 4 hydrogen atoms here, and those get rearranged into the 2 waters. And I'll put 4 dots on the oxygen here. Okay, then I look at this here, and I have 1 carbon. 1 carbon gets placed over there. I got 4 oxygens, and I have 1, 2, 3, 4 oxygens here. So this would be an example of balanced chemical reaction. Now, we want to understand chemical properties a bit, and this reaction is called a redox reaction. A redox reaction because what we have is we have an oxidizer and a reducer present. There's going to be an oxidizer and reducer. And what are oxidizers? What do oxidizers want to do? Oxidizers want to take electrons. And so, which of these is the oxidizer, the methane or the oxygen? It turns out the oxygen is the oxidizer here. The oxygen, because oxygen, what does oxygen want to do? It wants to take how many electrons? If oxygen wants to take 2 electrons, so this is what's going to happen. So when we analyze this, we got 4 oxygen atoms. That's it. Each of these oxygen atoms has no charge. But when we go over to CO2, we can imagine the oxygens. We got 2 oxygens at 2 minus. That gives us a carbon at what? Well, unfortunately, we're out of time, so I'm going to stop shortly. But what would the carbon be here? If the oxygens are, it would be +4. I'll put it Roman numeral because having a +4 charge is pretty tough. And so then this would add up. The -2 minus 2 plus 4 gives us 0. That's the charge on this. 0 plus 0 gives us 0. 0 plus 0 gives us 0. Over here, the oxygens did what? When we look at it, 2 of the oxygens ended up here. And so those 2 oxygens went from a 0 to a -2. And so how many electrons did these 2 oxygens gain in total? +2 for that, +2 for that, so that's +4 electrons. And then 2 of the oxygens end up in water over here. If I look at water, water is an oxygen with 2 hydrogens. And if we visualize the oxygen as being O2 minus, what does that leave the hydrogens as? +1. And so 2 of the oxygens end up in water, and the waters are both the same, so we're going to have H plus, and an O2 minus. And so basically what we're going to have is another 4 electrons. And so those 2 oxygen molecules have to gain a total of 8 electrons total. All right, I'm out of time, so I'll stop here. I'm going to continue talking about this reaction in more detail next time.